Okay, I guess we are ready to start. Good afternoon and welcome everybody to today's seminar on sustainable development. We, as you know, those of you who are following that seminar series know that we try to actually, select topics that are timely or that have come up in the public discussion or in the scientific discussion recently. And so a few months ago, geoengineering came to the public and scientific attention mainly through the release of the NAS reports, National Academy of Sciences reports on geoengineering with recommendations for how to go about it and discussing primarily the pluses and minuses, risks, opportunities, etc. of CDR, carbon dioxide reduction, and SRM, solar radiation management. So at that time, we thought this would actually be a great topic for us to discuss, and we started to put a group of experts within and from outside Columbia and US Institute together, because all of them are busy. It took us a while to put it together, but finally we managed, and it's a great pleasure to welcome for today's seminar Richard, Alan, Mike, and Scott. And the way we will go about that, as usually, I will introduce Richard Seeger, who will then moderate the session. It's about a 2-hour session. You will have introductory talks, and then there will be plenty of time for discussion of the topics. So let me introduce Richard Seeger, who is not an unknown to many of you. He is the Palisades Geophysical Institute Lamont Research Professor, works at the Lamont Doherty Earth Observatory of Columbia University. He's also a member of the Earth Institute faculty. Richard has been here since a long time after leaving Liverpool University. He came here in '83 and took up his studies at Columbia University. He got his PhD in Earth Environmental Sciences in 1990. And then he left us for a little bit, I think, to the University of Washington for a postdoc, and came back to return to Lamont and continue his career. Richard is studying climate variability and change on seasonal and longer, reaching to glacial, interglacial timescales. He uses climate models, instrumental records, and proxy reconstructions to do that. Most of his focus is actually on hydroclimate, hydrometeorology, the drying out of the west of the United States. You might have seen some of his work in the press or in scientific publications. And he is, of course, concerned about how that connection will evolve as climate is changing, which links it directly into the question of what do we have to do about our climate, and brings us to the topic here, geoengineering the Earth's climate, risks, opportunities, and governance challenges. So I would like to invite Richard to the podium to moderate this afternoon's sessions.
All right, thank you very much, Peter. The way this is going to work is we have 3 speakers, Scott, Alan, and Michael. Alan will go first, and Scott will go last. And the point here is to try to cover both the geophysical aspects of attempts to geoengineer the climate and what can be achieved by that and what cannot be achieved by that and the risks, but then to go well beyond just the physical science of the problem to address issues, legal aspects and international treaty aspects of this particular problem. So the speakers will each talk for about 20 minutes, and I'll take about 1 or 2 questions while the next one gets set up. So we should be able to leave, and I'll make some introductory remarks about why we're doing this. But this should leave about 45 minutes at the end for a good exchange, because my experience is that a lot of people have a lot of questions and they like to ask them about the question of geoengineering. So the point is to really try to get an exchange. So if you don't get a question in between, wait until the end and you'll have plenty of opportunity then. So as Peter said, the proximate cause for why we're having an event about geoengineering now is that earlier this year, the National Research Council, which works for the National Academy of Sciences, released two quite lengthy reports on climate intervention, and that was divided into two different reports. The first one, the one on the left, deals with the issue of carbon capture and sequestration. So that's an effort to remove the carbon dioxide from the atmosphere and store it somewhere, for example, in rocks where it can be out of harm's way. That at least addresses the problem of climate change, because climate change is being caused by the addition of carbon dioxide primarily into the atmosphere, which absorbs long-wave radiation that otherwise would escape to space, warming the planet. The other report that they released was reflecting sunlight to cool Earth, which normally is referred to as solar radiation management. So this doesn't directly address the cause of climate change, because it doesn't address the carbon dioxide in the atmosphere. Instead, it's a proposal to offset some of the warming caused by carbon dioxide by instead increasing the reflection of radiation to space, which can be done in a number of ways, but the most common way that is proposed is through injection of sulfate aerosols into the stratosphere. So of these two methods of geoengineering, the one on the right, the solar radiation management, is definitely the one that is more controversial, and that is the one that we will primarily be focusing on today. Carbon capture and sequestration presents its own problems, but we will focus the one on the right. In some ways, the one on the right, solar radiation management, is actually the easier one to do right now. So the National Research Council did admit that albedo modification presents poorly understood risks, but then they did make some recommendations, and I've just printed them out here. They did recommend that albedo modification at scales sufficient to alter climate should not be deployed at this time, but they did recommend that a albedo modification research program be developed within the United States and implemented that emphasizes multiple benefit research that also furthers basic understanding of the climate system and its human dimensions. They also recommended that the US improve its capacity to detect and measure changes in radiative forcing and associated changes in climate. That's a very good recommendation, because right now our ability to measure the radiation budget of the planet is insufficient to tell if an experiment like this was done, to tell whether it was really working or not. So that's a very good recommendation. And then the final recommendation that I've listed there, I think there were others, however, is that the initiation of a serious deliberative process to examine what types of research governance, beyond those that already exist, may be needed for albedo modification research, and the types of research that would require such governance, potentially based on magnitude of their expected impact on radiative forcing, potential for detrimental direct and indirect effects, and other considerations. And these are the issues that Michael and Scott will be addressing later. So why is geoengineering being discussed at all? It is because of the path that the Earth is on in terms of climate change. We are already at 400 parts per million by volume, and global emissions are increasing, not decreasing. It's often thought that a warming of 2 Kelvin above pre-industrial temperatures is sort of a wished-for upper limit of what we would consider remotely acceptable. If we think that, we cannot really, as the top figure shows, which is equilibrium temperature change for CO2 equivalent radiative forcing, we can't go above 450 parts per million without having a less than 50% chance of the temperature change being less than 2 degrees. So we're essentially already there. We're very, very close to being there already. If we were to do that, the bottom red curve on the right, which is emissions, you would see if we were to try to keep emissions, CO2 levels below 450, we would have to start reducing CO2 emissions rapidly right now. We've kind of emitted about half as much CO2 as you would be allowed to if you were to keep temperatures below 2 degrees. So that's why the curve looks like it goes up and it goes down. But of course, we're nowhere near, by the same amount. Of course, we're nowhere near that, and instead, the blue curves are various emission scenarios that have been used for IPCC purposes that are based on economic modeling and so on. All of them go up. So even a 2-degree temperature change is enough to cause serious climate disruption. This is a figure from a paper by Susan Solomon, where she plotted the change in precipitation around the world per degree of global temperature change. And you can see that in key subtropical regions of the world, for example, the Mediterranean stands out. You're talking about 12–15% reductions in precipitation per degree. So per 2 degree, you're talking about a significant amount. So 2 degrees might be sort of a sense that we wouldn't want to go beyond that. Where we are already is making it seem impossible to avoid getting to that point, but that will already involve what we will probably look back on or think of when we get there as rather unfortunate and disruptive climate change. So given this trajectory, this is why the issue of geoengineering the climate either by carbon capture or by solar radiation management has become a very seriously considered additional range of portfolios to deal with climate change. Okay, so that's the background as to why we are here. And our first speaker then is Alan Roebuck. Alan is the Distinguished Professor of Environmental Sciences at Rutgers University over there in New Jersey. He's had a very long career, is really the go-to person on the study of volcanoes and climate, and has also been very heavily involved in climate model simulations of geoengineering in recent years. He has many feathers in his cap, but this year he's the 2015 Jewel Charney Award recipient from the American Meteorological Society, recognizing his role in the study of volcanoes and climate and stratospheric aerosols and climate, and also the role of soil moisture in climate. So I will hand it over to you now, Alan.
Thank you very much. I'm going to talk about geoengineering or sunblock with consequences. Here's the situation we're in. We want to be happy, so to be happy we get stuff, and stuff requires consumption of energy, and if we burn fossil fuels it produces CO2 emissions. Now this leaves about half the CO2 in the atmosphere that we burn, and this causes climate change, and this has impacts on humans and ecosystems, and this has a negative feedback back on our desire to be happy. So how do we break this cycle? We could have less stuff, we could use energy more efficiently, or we could produce energy without using the atmosphere as a sewer for CO2. These are all green. That's called, or we could try and take the carbon dioxide out of the atmosphere once it's in, or we could do solar radiation management. These are the two things which are labeled geoengineering. Absent all of those, we'll have to adapt to climate change. And absent that, we have suffering. Those of you taking pictures, by the way, this is on my website, so I'll make it freely available to you afterwards. So I'm going to talk about solar radiation management. What is geoengineering? It's defined as deliberate large-scale manipulation of the planetary environment to counteract anthropogenic climate change. So it refers to large scale. As Richard said, the National Academy just released this report on climate intervention. It was mostly funded by the CIA. And it talked about these two areas. CDR is probably a good thing, but it's very expensive. SRM, Richard said it's easy. I'll show you why I'm not sure that that's the case. Why did they call it climate intervention? They said, first of all, geoengineering is this picture on the right. It's digging earth out. And And if you call it climate engineering, engineering sounds like you know what you're doing and you have control. So they chose the term climate intervention, which means you're an action intended to improve the situation, but you're not quite sure what the impacts will be. So, but people have called it geoengineering for a long time, and so the question is, will the term climate intervention go into common use? It's not a new idea. Here's a figure from a paper in Nature in 2001 showing these different ideas by David Keith, both the reflecting sunlight and capturing CO2. But it wasn't until Paul Crutzen in 2006 wrote a paper about this, and he has a Nobel Prize in chemistry, that he said, I don't see any mitigation going on. Maybe we should consider geoengineering. And people then sort of were free to do research on this. And it really started a lot of research just after that. Here's our global warming that we know and love, produced down the street at NASA GISS. The part of the explanation of the warming of the first half of the 20th century was recovery from volcanic eruptions. There were a lot of them at the end of the 19th century. After World War II, there was a lot of pollution of the troposphere, a period we call global dimming. And after the EPA was established, the atmosphere didn't get any dirtier, and the greenhouse gases have dominated. People have looked at that and say, if volcanic eruptions can actually cause cooling, why don't we do that on purpose? If particles in the lower atmosphere can reflect sunlight, why don't we think about doing that? And this is the idea that go into the solar radiation management. The four ideas, one is space-based reflectors, which people think is very expensive and uncontrollable, and there hasn't been much work on that. The one that's gotten the most work is creating a cloud in the stratosphere like volcanoes do. There's another idea of taking clouds in the lower atmosphere and seeding them to make them brighter over the oceans. And finally, there's the idea of brightening the surface by painting roofs white or engineering crops. And that turns out it would not be very effective, and things will keep getting dirtier. So the two ideas in the middle are the ones that have gotten the most attention, specifically stratospheric aerosols. Here's a picture of where we live. So this is Long Island. These white lines in the clouds are called ship tracks, and ships sailing under them emit particles and SO2 and heat, and they make the clouds brighter. And so the idea of cloud brightening is to do this on purpose to make clouds brighter. This is the ship invented by Latham and Salter. It would be powered by the wind, and it would pump seawater out in little droplets that evaporate, and the salt would go up into the clouds and make more particles, but smaller ones, and they would be more reflective. Although it turns out we're not quite sure how effective that would be. There's a new idea of taking cirrus clouds, the high clouds in the atmosphere that on the average warm, and if you put ice crystals, nuclei in there, there would be fewer of them, and that would let more heat escape. So the clouds would reflect less sunlight, but they would also let more heat escape. And if you do it just right, you can actually cause cooling. So they've done a calculation. This is the effect, this is the amount of particles you put in. You get cooling and you get warming, and if you do it just right, you get a little bit of cooling, but if you do it too much, you get warming. So this has the potential maybe for 2 watts per square meter, which is about half of doubling CO2. So people are looking at this idea now too. How do you get the particles up into the stratosphere? You could use artillery, you could use balloons, you could even build a tower, or you can fly them up with airplanes. And we calculated how much it would cost, and it turns out airplanes is probably the cheapest way to get sulfur gas up into the stratosphere, and then it would react with water and form sulfate aerosols and produce the cloud. But if you wanted to do it tomorrow, you couldn't. This technology does not exist. There are no planes that can do it. With tanks, there's no way to do it. Or there's nothing to brighten clouds out in the ocean. Even if we could get the gases up there, we don't know how to produce particles of the right size. When you spray more SO2 into a cloud, rather than getting small particles like we would like, theory tells us the particles would grow and you get larger ones. But putting sulfur gases in the lower stratosphere using existing military planes would cost a few $1 billion per year per teragram or million tons of sulfur. Now, some people claim that geoengineering, as Scott did, is cheap and easy, that solar radiation management is cheap and easy. But I don't think that that's true. And so I just want to show you some evidence for that. First of all, if you evaporate seawater, as it evaporates, it cools, and the particles would then sink. Can you even get them up into the clouds? That's not been demonstrated. Also, if you seed the clouds, this is a climate model simulation, you sail a ship across, you might get brighter clouds here, but next to it you would get sinking motion, and that would evaporate the clouds, and the net effect might even go the other direction. So it depends a lot on what the existing cloud system is and exactly how much you seed, and nobody's figured out exactly how to do that on a robust way. So it may not this cloud seeding may not even work. How do you use airplanes to get the gas up? Well, you could put sulfur back into the jet fuel, but the planes don't routinely fly that high except in the Arctic, into the stratosphere. You could have tanker aircraft carry it to the stratosphere. You could have fighter planes carry it, but you need a lot more planes. Or have tanker aircraft carry it to the upper troposphere and have fighter jets carry it the rest of the way. Or have maybe have a tanker tow a glider with a hose. These are ideas, but nobody's ever done it. So I did a calculation. These planes, these tankers are being replaced by new ones. And so with 3 flights a day, operating 250 days a year, you could get 1 teragram of gas into the stratosphere. Now, David Keith had a group that also calculated, I did a very back-of-the-envelope calculation, and they designed a new airplane to do it, and it turns out that they got the same estimate of several $billion a year to get 1 million tons of gas up into the stratosphere. So how much would you need? So it turns out that theory tells us you get larger particles rather than more if you keep spraying SO2. And they would fall out more quickly, and they would also be less effective per unit mass in reflecting sunlight. So there's Patricia Heckendorn showed that. My original calculations of putting 5 million tons of sulfur in, 10 million tons of SO2, caused a cooling of about almost 4 watts per square meter, enough to counteract doubling CO2. But when she allowed them to grow, you got a much less effective, and even 20 million tons of SO2 per year didn't get that much cooling. There's a new paper by Niemeyer and Timrek, which just came out, and they said a solar radiation management strategy required to keep temperatures constant at that anticipated for 2020 whilst maintaining business as usual conditions will require atmospheric injections of the order of 45 teragrams of sulfur per year, which amounts to 6 times that emitted from the Mount Pinatubo eruption each year. So Mount Pinatubo put about 20 million tons of gas into the atmosphere once, so you need to have 6 of them every year. And that would be, instead of 1 teragram of sulfur, you would have 45 teragrams of sulfur, so that would be 45 times $10 billion, times $5 billion. So now you're getting to real money. So it might not be that cheap or that easy. Just after Crutzen's paper was published, there was a meeting at NASA Ames to the first meeting on geoengineering. And this Rolling Stone came out that week, and across the top, Dr. Evil's plan to stop global warming. And inside there was an article about Lowell Wood from Livermore, who, he's this big guy, he's a physicist, and he said, I'm smarter than all you, I'm a physicist, and I made the H-bomb, with Edward Teller, so we're just going to create particles just the right type, and they're not going to destroy ozone, and they're going to reflect sunlight, and we're going to put them exactly where we want them so they won't cause regional climate change. And I said, Lowell, there's one thing you've forgotten. It's called wind. Oh, no, well, I'll figure it out. So he was really excited about this, and these engineer and physicist types were really excited. And so I started writing down these reasons why it might not be such a good idea. And I ended up with 20 reasons why it might be a bad idea, and now I'm up to 27. This paper was published in 2008. And so I think, though, each of these needs to be quantified so society can make informed decisions about whether or not ever to implement it. The one benefit is if you could create a cloud, it would reduce surface air temperatures, which could reduce the negative impacts of global warming. Will we have to live with all of these risks in order to get this? That's the question. The diffuse radiation would increase plant productivity, increase the CO2 sink, you'd have beautiful sunsets. But you might cause drought in Africa and Asia, perturb the ecology, deplete ozone and more ultraviolet. It wouldn't do nothing to stop ocean acidification, which by itself is a reason to stop putting carbon dioxide in the atmosphere. It won't stop the ice sheets from melting, because in Antarctica especially they melt from the bottom. It have impacts on tropospheric chemistry. You wouldn't have blue skies anymore, less solar energy generation. Rapid warming if you stopped it. You couldn't stop it quickly if there was a big volcanic eruption. Or people could make mistakes. Was anybody in a car today? Did you have your seatbelt on? Okay, well then you understand this concept. Anything made by humans, operated by humans, can fail. So would you trust the only planet known to sustain intelligent life to this one very complicated technical system? There'd be unexpected consequences. There'd also be unexpected benefits. Would you like a big company, a BP Geoengineering Corporation, or would you like it could be used for military purposes? And then there might be disagreements. How do you set the global thermostat if you could do this? For you young people, this is how we used to set thermostats. People in high latitudes might want it a little bit warmer. People in islands that are now sinking would want it a little cooler. How would you even agree on that? And there's a treaty, I think we'll discuss that, the ENMOD treaty and maybe other treaties, and other things. So how do you test these things? Well, we started this climate modeling project called GeoMIP with standard calculations done by all the climate modeling groups in the world so we could compare the results. And we're having our 5th workshop this summer, so it's been going for 5 years now. And I'll just show you a couple results. We asked all the models to take quadrupling carbon dioxide and balance it by turning the sun down. And so if you do that, you can keep the global temperature constant, but you cool the tropics and you warm up the high latitudes. That's because there's a lot more sunlight in the tropics than at high latitudes. And so if you're worried, say, about Greenland or Antarctica melting, you're still going to get some warming, so you have to overcool the tropics if you're going to do it on a global basis. We also looked at the impacts on precipitation. So if you look at the monsoon regions of the world, these are regions where most of the precipitation comes in one season. So in particular, India and China have a strong summer monsoon. If you cool the land, if you cool the earth, the land cools more than the ocean, and it's this temperature difference that drives the monsoon. So you'd actually have weaker monsoons. So we had the models do this for different regions, and I'll just show these. These are the experiments. The monsoon precipitation in India and East Asia would go down. Now we can use volcanoes as an analog and look at what happened after the Mount Pinatubo eruption, which was the last large volcanic eruption in 1991. And for the year afterwards, there was a reduction of precipitation over India and over China. And the Amazon too. And so that analog can test this theory. What about if you stop? So this is, we increased CO2 by 1% per year for 50 years, and then we stopped the geoengineering. So this is the results. The dotted lines are the global temperature for increasing CO2 1% per year. The solid lines are turning the sun down gradually to counterbalance that and then stop. What if you're doing geoengineering and there's a big drought in China or a big flood in Pakistan? They say, you damn geoengineers, you're doing this, stop it. You can't prove it. There's always droughts. No, I demand you stop. I'll shoot your planes down if you don't stop. And so you stop, and all the CO2 that's there rapidly causes warming, and you have climate change at a rate 10 times the rate you would get if you did nothing. This purple line is the BNU model from Beijing Normal University. They didn't actually reduce the sun that much, and so they got a moderate increase of temperature. Now for precipitation, you actually get a reduction of precipitation once you keep the temperature constant. And this, we understand this because the CO2 makes the atmosphere more stable and counteracts the effective evaporation. The BNU model has constant precipitation, so you can't control both temperature and precipitation at the same time. So I've outlined in red here now these things that can be addressed by GeoMIP and other climate modeling. Some of these things we can test with these theoretical models that have been tested on other causes of climate change, but some of the things we can't. We can use volcanic analogs to test some of the other things, some of the same things and some of the other things. And so we think we understand some of these by using either models or analogs. But some of them you can't test either way. How are we going to inform policymakers about these risks how are we going to figure out how risky it would be for these other things? Even the ones we can test, maybe the drought would be too much of a problem, ozone depletion might be too much of a problem, we might decide not to do it basically because of that. But there's all these other things, and so I think we really have to quantify all of these things so policymakers can make informed decisions. Now, one of the impacts is beautiful sunsets, because the setting sun reflects off the bottom of this cloud in the stratosphere, and the blue has come out because the people farther to the west got a blue sky, and all that's left is a yellow and red, and it reflects off it. This is a drawing done by William Ashcroft after the Krakatoa eruption over the Thames in London. The question is, if we do geoengineering, will the sky look like that, or will it look like that? Thanks very much.
Is there one or two quick questions for Alan, who kept to his time very well? Yes.
SO2, if I'm right, if it fell back into the lower atmosphere, it's a local pollutant, isn't it?
Yes. So when we burn fossil fuels, when we burn coal and oil, sulfur is a contaminant, and it produces SO2, sulfur dioxide gas, and that's the primary cause of haze in the atmosphere, and it's the primary cause of acid rain. As a byproduct of burning fossil fuels, we produce about 100 million tons of SO2 per year. Anyway, so if we add 5 million tons, it wouldn't be that much. If we add 90 million tons, because it's 45 teragrams of sulfur, so 90 million tons of SO2, then it would double the amount that we're already putting in. We did a calculation for much less, and it turns out even in pristine areas, the small additional amount of sulfur wouldn't be that much of a problem, and that was one of the things I crossed off my original list. It also ends up in the ocean, and the additional acidification of the ocean from CO2 is much larger than the effect from sulfur. So we don't think that that's one of the main considerations, although it does add to health effects oh my watch is telling me, okay. I get a new Apple Watch, so it told me it's 20 minutes. Yeah, so we don't think that that's a major consideration, although there would have small effects, but it wouldn't be as serious as the others.
And there was a question down here, Jason.
Alan, so a lot of your calculations, the GeoMIP simulations, as well as the calculations that you did for the amount of particulates that would need to be injected are for these end-member scenarios where you're assuming that you're counteracting the CO2 effect entirely with the sulfate modification. But people like Keith certainly argue for intermediate scenarios in which we reduce the rate of warming with these kinds of solutions, or maybe use it as a transitional option while other CO2 mitigation efforts are also used. Obviously, some of your concerns still relate to that, but how do you feel about these intermediate options as alternatives to this sort of end member that you presented?
David Keith's book says we should gradually increase the stratospheric gas a little bit and stop every once in a while and see if there are any negative effects, if we have any negative effects. But there's faulty logic in this. If there is some extreme weather after 5 or 10 years, how do you know what would have happened if you hadn't done the geoengineering? Because you're perturbing a little bit, and you already get these extreme weather events. So how do you know that it was caused by geoengineering? Maybe you have a perfect model that tells you what would have happened if you hadn't geoengineered. then just use the model. You don't have to do it in the real world. So I went to a summer school he organized last summer. I was trying to explain chaos to him and other people, that there's so much natural variability, and we wrote a paper in Science several years ago pointing this out, unless you hit it really hard and wait for several decades, only then can you get good enough statistics to see whether the new climate is different from the old one. A small perturbation, you won't be able to tell.
While this is being set up, I'm going to talk about the laws that do or might be applied to geoengineering, and I'm going to talk about some of the liability implications in case someone undertook geoengineering and it went poorly and somebody wanted to sue somebody else for that. So no laws have been enacted anywhere that are specifically designed to address geoengineering. But there are a number of laws that could apply. At the international level, of course, we have the United Nations Framework Convention on Climate Change, and following from that, the Kyoto Protocol.
What?
If you go to date modified, that would be the most recent one, and be the most recent one. So the United Nations Framework Convention on Climate Change, following that was the Kyoto Protocol. If all goes well, coming in December, we'll have a Paris Protocol or Convention or something like that. And, but it does not look like that is likely to address geoengineering. That is not really on the agenda. There is, okay.
I know, but sorry about that.
There is something called the Convention on the Prohibition of Military or Any Other Hostile Use of Environmental Modification Techniques, called ENMOD. That is an international treaty that was enacted in the wake of the Vietnam War after hostile efforts at weather modification. And its purpose was really to address military uses with that intent. And so it would not apply to geoengineering because that would not be its intent. Then we have something called the Convention on Long-Range Transboundary Air Pollution, which could be applied here if you had the necessary protocols. It is an international agreement that just sets up a framework but allows for various agreements to be written that apply to particular conditions. It does not now, there's not now one that applies to geoengineering, but thank you. But one could imagine that being created. Montreal Protocol is the international agreement on ozone depleting substances, and one based on the Vienna Convention on ozone depleting substances. So one could imagine modifying it so that it applies here. So all of these are existing agreements that with some modification could apply to geoengineering. Then there is international customary law, the law that emerges over the years from court decisions, from international agreements and so forth. And one basic principle is that no country should be allowed to emit pollution that damages another country. And also a variation of that, much more moderate, is that at least if a country is going to do something that could environmentally affect another country, it needs to do an impact assessment so at least it knows what it's doing. But these are not really, these are principles, but there's not really a ready way to enforce them except under some circumstances that I'll be talking about. And finally, there's a whole body of human rights law which says that states shouldn't undertake efforts that hurt a lot of people in specific ways, so that's a very general law, a set of laws that could be applied, but again, enforcing them is much more difficult. So these are all international agreements. At the national level in the United States, the Clean Air Act could probably be applied to regulate geoengineering by the U.S. or entities subject to U.S. jurisdiction. Clearly, these sulfates could be defined as air pollutants. You'd have litigation over whether it applies. If it's injected into the upper atmosphere, does that count? But at least there is a law that could be applied. clearly applicable if the U.S. were to undertake or approve or finance an effort would be the National Environmental Policy Act, the federal statute that requires environmental impact statements before major federal actions that could have an effect on the environment. So geoengineering would be the mother of all environmental impact statements if it were undertaken by or approved by the federal government. There's a federal statute called the Weather Modification Reporting Act that says if anybody engages in weather modification, they have to report it, but that's it. It doesn't regulate it. It's purely reporting. The president would have certain emergency powers if horrible things were to happen, and that would you'd have to figure out what that applies to. And then finally, many of the states have state weather modification laws, which were clearly designed for much, much more local things, and they require not only reporting, but in some cases licensing if you're going to engage in weather modification, although clearly they didn't intend to apply for this. So these are the U.S. laws. Many other countries have their own laws. No other country has adopted laws specifically on geoengineering. Now, as we've just heard from Alan, lots of bad things could happen. Some good things could happen, but lots of bad things could happen as a result of geoengineering. And so the question would arise, if somebody got hurt as a result of this, could they sue somebody? There are plenty of legal theories that could be used as a basis for this kind of litigation. The most likely would be a public nuisance or private nuisance, which are long-standing based on the English common law. Basically, if you pollute your neighbor or even a distant neighbor, you can sue them for damages. And there are various other theories that are available. But there are some very significant challenges and obstacles that would arise in such a lawsuit. First question would be proving that the bad things that happened were as a result of the geoengineering. In particular, if we had a change in precipitation or in typhoon, monsoon activity, or any of that, and some other country experienced that and they wanted to sue for damages, a question would be, what would the weather have been in the absence of geoengineering? So we are testing the limits of weather forecasting or weather hindcasting, trying to figure out what is the baseline, what would the weather have been but for this event. So the science of attribution has certainly been improving, and there are better, more sophisticated methods to figure out what kind of weather events were influenced by various activities. But this would really be testing the limits of that. And one question that would be very important here is, what is the burden of proof? Does the plaintiff have to prove that the injury that they suffer was more likely than not caused by this activity? 51% chance? Was it beyond a reasonable doubt? Is it 99%? Is it somewhere in between? So the magnitude of the burden of proof will have a big impact on who would win this litigation in terms of how firmly you have to establish causation. A second major question would be, in what court do you go? In what forum do you go? We do have an International Court of Justice, which sits in the Peace Palace in The Hague, built by Andrew Carnegie around 1910 in an effort to avoid war, which didn't really work. Only some countries have signed on to the general jurisdiction of the International Court of Justice. The U.S. is not among them. The U.S. has subjected itself to their jurisdiction for things like boundary disputes, but not in general. The International Court of Justice really is set up to hear disputes between or among states. And depending on what states are involved, the ICJ may or may not have jurisdiction. If it doesn't, because the particular defendant country that is involved isn't subject to it, then it's not clear where they would sue. There are some other specialized tribunals that have been set up. There's an international tribunal on the law of the sea and so forth, but it is that probably wouldn't apply. Now, there's a whole other set of legal regimes that would apply to ocean iron fertilization, which is another type of geoengineering that we're not talking about this afternoon. So these are two colossal barriers that would arise in any litigation. In addition, who is the defendant? How do you get jurisdiction over them? In many settings, government agencies have sovereign immunity. They need to have waived that sovereign immunity in order to be sued. Would that apply here? If what we're doing is if there were, let's say, in the U.S., an effort to undertake geoengineering and some environmental or other group wanted to stop it in court, there would be the same kind of obstacle to that has proven fatal to the efforts to assert common law liability against greenhouse gas emitters, which is that the U.S. Supreme Court has held that when Congress enacted the Clean Air Act, that gave EPA the power to set greenhouse gas emission limits, and that is solely EPA's job. It is not the job of the courts to come up with the appropriate levels of emissions. Similar kinds of questions, sometimes called separation of powers questions, sometimes called political question issues, could arise if you had a governmental policy to go forward with it. And then there's some other issues that would arise in the litigation, clearly. One issue, if money damages were sought, is money damages as of when? And is it as of the date of the lawsuit? Are you going to try to project the money damages 20, 30 years out? How far is it going to go? How are you going to calculate all of that? Who would you sue? Who would sue and who would be sued? So most international public law litigation is between countries, between states, and so they could sue each other. What if you had a damaged party that was a company, a big agricultural operator or water supplier or something like that? Could they sue as a plaintiff? Could a lot of individuals get together and sue in the nature of a class action, which the U.S. courts recognize and some others do as well? Would you set up some special international body that would be given the jurisdiction to be the plaintiff? That if somebody engaged in a geoengineering effort that caused widespread damage, would you designate the UN Geoengineering Agency or someone like that to be able to bring these lawsuits and collect and disperse the money? Who would you sue? So if it were authorized by a state, you would sue the state and seek its damages. What happened if you had some private entity that on its own, without any particular governmental blessing, went off and did that? Then you would have a whole lot of other issues that could arise. Now, there are a number of special compensation and liability systems that have been established, mostly by treaty, in order to resolve these liability issues in particular instances. So there is a space liability convention that basically says that if you launch a satellite or a rocket and it falls and hits somebody on the head, who's liable for it? And there's strict liability, and that's very clear. There is an International Oil Pollution Compensation Fund, which has been established that requires certain oil tankers to put money into a fund, and they have a way to disperse it. The National Vaccine Injury Compensation Program set up a special body that's colloquially known as the Vaccine Court. And if somebody claims that they are injured by a vaccine, they can go to that special court, and a fund has been established from the vaccine manufacturers to pay them. So we have a number of things like this. So there is ample experience in setting up special tribunals and special funds. The difficulty is that in most of these cases, you don't have a massive causation issue. If a rocket hits you on the head, you pretty much know what rocket it was and who launched it. Similarly, with a massive oil spill, you know where that came from. Now, you'll get into causation issues with the vaccine issue, but at least you usually know who the vaccine came from. You have litigation over whether the person who got sick as a result of that vaccine. But you don't have nearly the sort of causation issues that would arise in geoengineering. But if a geoengineering scheme really were to be developed, I think it would have to set up in advance a liability scheme. So we know what the rules are, we know who can sue whom, we know what the standard of proof is, we know what court will hear it, we have some fund to pay it out. The final thing I wanted to say is that if you had in domestic litigation in the U.S., if the U.S. were to try to undertake this kind of activity and people wanted to stop it, they could go to court and try to have the approvals that were granted taken away, or have it go back to the agency that approved it to think about it again. They could seek an injunction that would stop the action. They would seek money damages, and they would try to enforce it. So all that is conventional at the domestic level, but expanding this to the international level is extremely challenging. So the bottom line is that there is almost no law that really does apply. There are lots of laws, lots of legal concepts that are out there that could be applied, but working it all out and trying to come up with some international agreement will be a phenomenally challenging task. And to explain that task to us, we have one of the world's leading experts on such negotiations, my colleague Scott Barrett.
Where is the funding coming from on these funds that are supposed to provide compensation? Because if they're taxpayer funded, or are they corporate funded? Thank you.
They tend to be funded by the entities that are undertaking the activity. So the oil spill compensation fund will come from the parties that ship, the tankers, and the vaccine compensation fund would come from the manufacturers of the vaccines. Now, one interesting question with geoengineering is who would pay for that? Would it be the country that is undertaking the activity? Would you also assess, in addition to losers, there would be winners. There would be some places where you have more agricultural productivity than you would otherwise have. Do you tax them to try to recoup some of the benefits that they achieved in order to help pay for the victims? But of course, that'll itself be its own set of lawsuits because nobody's going to want to be taxed. But you need to, these funds tend not to come from general tax revenues. They come from a particular source.
One more.
You listed the continued ocean acidification as a potential problem. Why would that be a legal problem?
Why would ocean acidification be a legal problem?
Yeah, or more in general, why would not mitigated climate change be a legal problem?
I'm sorry, I'm not sure I understand. Why would not?
In my perception, I'd say any side effects of the geoengineering could be a legal problem.
Yes.
But this is not a side effect, it's just unmitigated climate change.
So if the question is why isn't unmitigated climate change a legal problem, well, obviously is a legal problem, and we have the international negotiations to try to resolve them.
Thanks, Richard, for organizing the meeting and all of you for coming. Now, Richard just mentioned this book I published in 2003. I went back and checked that book. The last chapter is about climate change, and I checked about whether I mentioned geoengineering in that book, because I knew about it. I never mentioned it. So why are we talking about it now? Oh, it's very clear. The reason we're talking about this now is that the world has done nothing to limit atmospheric concentrations of greenhouse gases. Well, they've done a lot. There have been a lot of meetings. And there are going to be more meetings, and they're coming up now, moving toward, they're in Bonn, I think, right now, negotiating, and they'll be returning to Paris very soon. We had the two co-chairs from Paris here a little while ago in a panel that Michael participated in with me. And I asked them, I looked at the text that had been negotiated in Geneva. It's a draft, it's full of brackets. But the only thing I could see in there that was novel was mention of including a review process. So countries are going to basically declare what they're going to do in terms of reducing emissions, and then there's going to be some kind of process. Basically, all this is meant to facilitate naming and shaming. And I asked the two co-chairs if they thought this review process would make a difference. These are the co-chairs for the meeting. And they said here, no. So this is why we're here talking about geoengineering. It's because we're not getting a grip on the problem of climate change. Now, my opening slide here shows you a cover of a famous book that's a work of fiction. But I think it's not a bad way to start thinking about this problem of geoengineering because it's so novel and unprecedented. And we are talking about the potential use of a technology that would change the relationship that humans have with nature. And I don't think we should do that lightly. There are a lot of people modeling not just the atmospherics of geoengineering, but also the governance side. And in many ways, I think it's a bit early days to be doing that. I think that when you think about geoengineering, it's helpful to compare it to the alternatives. It's cheaper. I'm glad I didn't say it was cheap, Alan. But it's cheaper than reducing emissions to the point where you can stabilize concentrations. It's quicker. And of course, when I say geoengineering, I mean the reflecting particles, reflecting light away by the means of particles mainly in the stratosphere is how I'm thinking of this. It'd be quicker. But it has a different effect on radiative forcing, so it's not going to do the same thing. It's really important to understand. It's not a perfect substitute for not putting something in the atmosphere that wasn't there before. Okay, it's not the same thing. It can control global mean temperature, potentially, but it can't preserve the spatial distribution of temperature. So it's not going to result in the same kind of climate that we're used to. It can't preserve the temperature, the precipitation, and sea level all at the same time independently. There are known risks, although I would point out there are also risks associated with cutting emissions. For example, a number of people are worried about nuclear power, and there are, of course, unknown risks that people are worried about. Let's compare geoengineering with another thing we could do, adaptation. Both can be done unilaterally. That's very important. The world is very good at doing things that are unilateral, whether those things are good for all of us or not. The world's very good at doing those things. Geoengineering is unlike adaptation, though. It would have global consequences. Now, there's a lot of interest in having adaptation financed by rich countries for poor countries, but you have to ask, what incentive do the rich countries have to provide that kind of assistance? And one thing to bear in mind about geoengineering is if it were used for rich countries, it would also alter the climate, possibly for the better, possibly for the worse, but for poorer countries. Adaptation is very different. Adaptation compartmentalizes the world. Let's compare geoengineering with direct air capture. Air capture gets at the root cause of the problem. Much better for that reason. It's actually the only true backstop technology we have for addressing climate change, but it would be very slow. And it would be costly. We don't know exactly how much, and I think we should be doing a lot more research into that, but it would be more costly, as I've understood, both technologies than the reflective particles. And because it would be more costly, you would need a number of countries to cooperate together to finance this massive project. And that means that there would be less of a governance problem because the whole thing wouldn't happen unless you had countries collaborating together to finance the project. And there are storage issues. Richard mentioned in the introduction storage in rocks, which would not be a risk, but there are other means of storage that could potentially be of risk. What are some of the objections to geoengineering? One thing to bear in mind about geoengineering is that we are already doing it. We just don't call it geoengineering. So if you think about reflective particles, there's a paper by Ramanathan and Feng arguing that half the warming associated with the rise in atmospheric concentrations of greenhouse gases is being covered up, masked by aerosols, particularly over China, which tells you, by the way, that if China cleans up that air pollution, there'll be a release of heat. My point is that we're already doing things that through reflective particles that we're not doing deliberately, but that are affecting the climate, and people aren't very upset about that. And why should we take something we're doing deliberately as being very different? And I want to emphasize this because the way in which people approach this problem I find is fascinating. You may be like me, you probably are, at least in this one respect. When I first heard of this idea, I thought, this is crazy. This is insane. And the more I think about it, and it's taken me a long time, I've started to look at it differently. And in particular, I've started looking into this question that has intrigued also people in the philosophical area and in psychology, about how we are concerned about something we do that's inadvertent and has a consequence versus something that's deliberate and has a consequence. And it turns out that this is how we are engineered. We have an aversion towards making certain changes that are deliberate. And I think that's partly what's going on with geoengineering. And for me, I think that's an emotional response, which I understand and which I share myself, but I would hope that we would make decisions about something this monumental based on rational thinking. Toward the bottom of Alan's list of problems with this approach was an idea called the moral hazard problem, which basically means that even if we just knew about geoengineering as a possibility to address this problem, we won't bother to address it properly. There are a number of things I wanted to say about this. This is normally, Alan didn't emphasize this, but this is often the complaint that's often made about, emphasized about geoengineering. First of all, this is not a correct use of the term. That won't interest most of you, so I'm not going to explain why. It doesn't matter. It could actually be an optimal thing to do in the sense that if geoengineering worked, it actually would be better not to waste a lot of money on reducing emissions, notwithstanding all the other problems. Of course, there are a lot of other problems. It's not a perfect substitute, so don't get me wrong. But still, letting off a little bit on reducing emissions might be a good thing to do. The fear that others might geoengineer in a way that you don't like might actually cause you to divert more resources towards reducing emissions. There's a colleague I have, Johannes Erpelainen in political science, who has argued this. The main point I would make about this, the free riding problem to reduce emissions of greenhouse gases is so powerful that I believe that the knowledge of geoengineering has had virtually no effect at all on human behavior. And the reason that all the negotiations in the past, Kyoto and Copenhagen and the next one in Paris and so on, the reason they haven't added up to much has nothing to do with people thinking there's a quick fix. So I don't think this is a non-issue, but the last thing I'll say about it is also an issue we can't do anything about. We do know about this technology, so we have to accept this. The other one that Alan mentioned is the sometimes called the termination problem. So if we start using it and we moderate the temperature, what happens if we stop using it? And this is alarming because temperature would rise very quickly. On the other hand, I think precisely because temperature would rise very quickly, it's probably unlikely we would stop using it. Now, some people have argued, well, there could be a catastrophe that would force us, in a sense, to stop using it. But if the catastrophe were local, this form of geoengineering, as I've understood it, is easy enough someone else could do it. And if the catastrophe is truly global, then at that point I think we'd have bigger problems to worry about. So I'm not sure I'm bothered by either of those criticisms. All right, so what do we do? There are four options that I'll mention here. One is we could just ban doing it. We just don't do it at all. And there's an environmental group, I think based in Canada, that has argued that. By the way, their webpage that argues we should not do geoengineering does not explain what we are going to do about climate change or what the risks are of climate change. I think that's very important. There's another group, and this is headed up by climatologists at the University of Cambridge, called the Methane Emergency Group. And their very afraid of methane release in the Arctic, and they think we should use geoengineering now and on a massive scale, because they're worried about this risk of so-called runaway climate change, which my understanding of the scientific literature is that other people are not concerned about this. The literature as a whole is not concerned about it. So those are two kind of polar extremes. There's another view that we should do the research, development, demonstration in some way now for possible use in the future, and often the idea of an emergency is mentioned. And finally, there's the idea that Alan mentioned of David Keith's, that we should sort of manage this. We sort of gently add some particles, we have some cooling effect, and meanwhile, he's having us bring down emissions. And my response to that would be, well, if we find the particles are working, why would we bother to bring down emissions? Or to put it differently, why would we be more inclined to control emissions when we're using geoengineering than when we weren't using it? Because remember, we're not doing it now. So I don't find that very compelling. Okay, geoengineering governance. Who decides whether this should be used, how it should be used, when it should be used, and so on and so forth? That, I think, is a central question. And the reason it's so important is because the economics, I wrote an article about this many years ago, the economics of this form of geoengineering are incredible. They're incredible because they're cheap, or I'll say cheaper. They're cheap, at least as I've understood this technology. I'm sure we could find ways to make it expensive, by the way, but still, compared to the alternative of limiting emissions, this technology would be cheap. If it weren't, it wouldn't be such a problem for governance. And it can be done unilaterally. A single country could do it. By the way, that country does not have to be the United States. There are lots of countries with the capability to do this, and given that it probably won't be done for quite some time, the number of countries capable of doing this is going to get greater and greater. And I think as we think about the governance issues, there are two big problems, and one is that we might use it when we shouldn't. That's the one that most of us think about. But I think there's another risk, and the risk is we don't use it when we should. And that's why I emphasized earlier this issue about whether our action to use it is deliberate or not. Well, Michael kindly said I knew a lot about international agreements, and I do, but we don't really have any on geoengineering, and that's why I started off with a book of fiction. I don't think we know very much, so let me just give you some real-world analogies that at least get close to us and help to think about it a little bit. One I'll mention is the testing of nuclear weapons. The first test ban treaty, called the Partial Test Ban Treaty, one aspect of this is that every country in the world was invited to be a signatory, but a number of countries chose not to participate. Those are the countries that decided they wanted to test their weapons. And the countries that did organize the treaty, the United States, the Soviet Union, and the United Kingdom, they moved on from above-ground testing to below-ground testing. The next nuclear test ban treaty, another test ban treaty, the Comprehensive Test Ban Treaty, was trying to address this by making sure that the testing, all kinds of testing, above or below the surface were banned, and that the treaty would only enter into force if all the nuclear-capable states ratified the treaty. Well, what's happened is for the Comprehensive Test Ban Treaty is a number of the nuclear states have not ratified. Of course, that includes the United States, but other states as well. So therefore, the treaty has not entered into force. It is not working. So you have a partial test ban treaty that limited the freedom of action of countries in the treaty that were not going to use above-ground testing anyway, and didn't restrict the actions of the ones who did want to use it. And then you have a comprehensive test ban treaty, which in the end has not really had much effect on limiting testing anywhere. Another example is from global positioning. So the U.S. has this global positioning system you are aware of. It makes it available to the world for free, but other countries are concerned that the U.S. retains the right to shut it off or control it in times of conflict. And it's not surprising that China and India are developing their own forms of global navigation, but also our allies, the European Union. They don't trust the United States. And now what's happening is you're going to have these different technologies in orbit, and the different parties are collaborating to coordinate their use of all these different satellites, so you actually can improve both systems. And I think this is what might happen with geoengineering, that what might happen is there won't be one person flipping the switch, which is how I think a lot of us have implicitly thought about it, but rather there'll be quite a few, because no one's going to trust the one who has his or her control of the switch. And therefore, the international agreement may not be just to restrain countries from acting, but also to coordinate the actions they take. Another thing is interesting, there is a committee, so this is a kind of a loose governance system on the GPS. The only members of the committee are the countries that have their own systems. So of course there's a small number of powerful states. But this committee was established under the auspices of the United Nations, and the developing countries are given a voice. They're not given a say, but they're given a voice, and the countries with these technologies are actually assisting these countries, the developing countries, to integrate the global positioning systems with their own technologies on the ground. I think the analog for geoengineering would be that there might be assistance on adaptation, where you would coordinate adaptation on the ground with use of geoengineering in the atmosphere and possibly elsewhere. The final example I'll give you is human cloning. There was an effort to negotiate a treaty against human reproductive cloning, but when this was being developed, the US and other countries insisted that another treaty be negotiated, or that the treaty include a restriction on therapeutic cloning. Well, the world is pretty unanimous in its support for a ban on reproductive cloning, but there is no agreement worldwide on a restriction on therapeutic cloning. And by requiring that the agreement cover both forms of cloning, the consequence was we don't have a treaty at all. There are no restrictions at all. And I think the lesson there is that if you're going to negotiate, I guess that blue is hard to see, if you're going to negotiate a treaty that is very restrictive, the countries that are most inclined to want to use that technology are simply not going to participate. The treaty won't be effective. So pulling this all together, geoengineering may be bad. I think most of us don't enjoy the prospect of geoengineering, but the alternative may be worse. This is extremely important to understand. None of us wants to do it, but the time in which we might do it, someone might do it, it would be very different. The circumstances would be very different. And in an emergency, people will ask for all sorts of things. I think geoengineering may involve a number of actions by a number of different players. The big challenge for governance is going to get the countries most inclined to want to do it, not to do it. And because the one good thing is, a bit like with nuclear weapons, because one country wants others not to have it, they may accept a restraint on their own freedom to have it. That's how the non-proliferation system works. Works imperfectly, but that's how it's, the logic of how it's supposed to work. And we're going to need something like that for geoengineering. And the big thing to worry about is the more you try to restrict what countries can do, the more the countries most likely to do it are going to just walk away. So what you actually want in an agreement is one that is, in a sense, is least restrictive. It's very important you have the fullest participation possible. Thank you.
Okay, Molly. I'd like to give a reality check. If you're to pull CO2 out of the air, which I strongly advocate, you have to, Scott said it would be cheaper and faster to do it by geoengineering. That's putting it mildly. If you wanted to balance our emissions today and you used 1 ton a day units, which people are thinking about, you would need, just to balance what we're doing today, 100 million of those.
If you deployed them at the optimal spacing, it would take up the area of all of Arizona. So this is big stuff. If you wanted then to not only balance today's emissions, but also to bring start bringing it down, if you made another 100 million of these, it would bring CO2 down at about 2 parts per million, 2.5 parts per million per year. So we wouldn't ever have the financial resources to bring CO2 down fast. So I think, I agree with Scott, like it or not, we've painted ourselves in a corner and we're going to have to use geoengineering to get through. Thank God I won't be here. Okay.
All right. Thank you, all three of you. That was all very, very, very interesting. I'd like to now open it to questions and just when you ask a question, make clear who the question is for. One or multiple people. Okay, who's going to go first? Yes, there.
As I see it, what you're dealing with is basically entropy. That is the second law of thermodynamics, and that's what's producing global warming. We're burning carbon dioxide. And the second law is basically there are so many more ways for things to screw up. It's Murphy's law than to go as expected. Over the long term, I mean, if we're talking sustainability, are we talking centuries? Is geoengineering a realistic prospect?
I think that so mitigation is reducing our emissions of CO2. And every scientist working on this topic says the solution to global warming is mitigation. We have to do that no matter what. And the only reasonable way to use geoengineering would be temporarily to shave off the worst impacts before we can get mitigation under control. The state of New Jersey paid for half of the solar panels on my roof, and I just 22 cents a kilowatt hour for renewable energy certificates, plus I get the electricity, and I haven't paid an electric bill for several years. And so I know mitigation's possible, and people will say, oh yeah, but you have a government subsidy. And I say, well yeah, that's right. that's the way it should be applied. And I think a gradually increasing carbon tax will have a huge incentive to rapidly reduce the emissions of CO2. The country of Germany has moved quickly from burning brown coal to having 30% of their energy from renewable energy already. So I think that there are a lot of people imply that we have to continue with emissions. There's no path toward reducing the emissions, and I think that can happen much more quickly than people think if there's a political will behind it. About the moral hazard, I think the moral hazard might actually work at reverse. When people say, what are you working on? I say, oh, geoengineering. They say, what's that? And I tell them about it. I said, you're thinking about doing something that crazy? Maybe global warming really is a problem. Maybe I should be more concerned with global warming than I was before.
Scott, did you have a comment about the feasibility?
Well, I think, what do you mean, technical feasibility or political feasibility? Yeah, I think they're different. I think we're moving in completely uncharted waters. This is completely unprecedented. This entire problem is unprecedented. And basically, I think the fundamental problem is with our institutions that were never designed to deal with anything like climate change. And reducing emissions is a real challenge because it requires complete change in technology worldwide when markets don't want to do it. There's a lot of cheap fossil fuel under the ground, and the temptation to take it out and put it up in the atmosphere is huge. And when a country accepts a cost to limit that, the benefit is spread around the world, and that one country gets just a tiny share of the cost, of the benefit. I think countries sincerely would be willing to take stronger action, but they need an assurance that everyone else will take stronger action. And that's what the treaties are for, and the treaties have never given that assurance. There's actually an article in the New York Times today about how you would enforce a treaty. It's actually one of the first pieces, to be honest, about where we are with climate change. Good one to read before the Paris meeting. And there are some provocative ideas of how we might bring about enforcement. Bill Nordhaus at Yale has the idea of imposing tariffs against countries that don't act. There are two problems with that idea. One is he's assuming that the countries that don't like this don't retaliate. Well, that may not be the way the world works. And another problem is, this is very important, that tariff he has only works up to a certain level of marginal cost, which is, I think, maybe $50 per ton. But the cost of bringing emissions to zero, which is what you need to do to stabilize concentrations, is going to be a lot higher than that. The air capture cost, we don't know exactly what it's going to be, but probably will be quite a bit higher than that. So we don't have a ready means to address this problem. And that I think, is what is going to take the entire international system into completely new territory.
I think the most likely scenario under which geoengineering would be exercised would not be because of an international agreement under the auspices of the UN, because I think it would be extremely difficult to reach the kind of agreement on a timely scale that would be necessary. I think it is more likely to happen if you have a country that is experiencing an utterly catastrophic event that kills an extraordinary number of people, and a huge amount of political pressure builds up within that country to do something. And if that country is a democracy, then even if the party in power doesn't want to do anything, a minority party would rise up and say, kick the bums out and we'll do it. Under one circumstance or another, I could imagine that being undertaken in that calamitous situation, and it won't be mostly the scientists who are driving that decision. It'll be mostly a political decision. If that were to happen, then the next time, and let's say it happens through a fleet of 747s spending months seeding the atmosphere, another country that felt that it was a loser as a result of this might want to stop it, and that is a prescription for military action, which none of us would want to see. And so I think it's because of that kind of possible scenario that's an especially important reason why we need to develop sooner rather than later some kind of international governance system to make decisions on who can legitimately in the world community do this and what happens if they act illegitimately.
I'd just like to say I don't think it's ever going to happen. An emergency. What is an emergency? There is no such